Today's lesson in environmental chemistry is topic 4, how much is too much? So in some cases, like if you're looking at a pool of water or something, it's obvious that pollution is present. And in some cases, it's not so obvious, right? If the body of water looks dirty and cloudy, maybe it's got some like algae or mildew or stuff floating on it, you'll know it's probably not a good idea to drink it. But in other cases, it's not so obvious. Like if we look at this lake here, in the Canadian Rockies, this is looks like a very clean lake, but it's still not recommended to drink from the lake because of the parasite Giardia that is present in the lake. So it's a parasite, and it causes like extreme intestinal illness, also known as beaver fever. So to drink from this lake, the water has to be filtered. It has to be boiled for at least 5 minutes to remove that parasite. So when we're talking about pollution, we're going to be also talking about pollutants. So pollutants, these are any materials or form of energy that will cause harm to a living organism. So it may be the result of physical, chemical, or even biological mechanisms that will threaten the health or survival of that organism. And pollution will be any alteration of the environment, producing a condition that is harmful to living things. All right, but the question is, at what point does the concentration of a pollutant become a problem? So many products used or bought, they have a standard way of indicating how much of a substance is present. So it could be percentage of weight or volume it represents. So for example, if there's 1% milk fat, that means that if it was yogurt, that means that in 1,000 grams of yogurt, it's going to contain 10 grams of milk fat. Or there's 1 gram of milk fat mixed into 10 grams of other substances that make up the yogurt. All right, so basically, so in the first one, it was 10 grams in 1,000 grams, which if you multiply after by 100, you would get it into percent. All right, so that gives me a 0.01, and then multiply that by 100, and that's 1%. All right, and then the same thing, it says 1 gram of milk fat into 100 grams of the other substances. Same thing, that'll give you 0.01, which is the 1%. Let's take a look at this example here. If the nutritional information label on a container of yogurt specifies that each 125 gram serving contains 7 milligrams of cholesterol, what's the concentration of cholesterol in a serving of yogurt in parts per million, so the ppm. So recall ppb was parts per billion, so here in parts per million is ppm. So the first thing we got to do is state the information as a ratio. So there's 7 milligrams of cholesterol in 125 grams of yogurt. That gives us 0.056 milligrams per grams. The next thing is we have to put it into milligrams per kilograms, and all we do is multiply that by 1,000. Okay, so that now puts us at 56 milligrams per kilograms. So 56 milligrams per kilograms is the same thing as 56 parts per million. All right, so the units have to be milligram per kilogram, which is equivalent to the parts per million. Okay, so the next part we're going to talk about is toxicity. The danger is in the dose. So when we talk about toxicity, this is the ability of a chemical to cause harm to an organism. So this harm can either occur directly or be caused by the substances that form in the organism as it uses up that chemical. So there is acute toxicity and there is chronic toxicity. So when we talk about acute toxicity, this is when just after one exposure to the chemical, there are going to be some serious symptoms. All right, an example is methyl isocyanate. This is an intermediate chemical made during the production of pesticides. It's also been used in the production of rubbers and adhesives, but it is a highly toxic and irritating material, extremely hazardous to human health. All right, so that is acute toxicity just after one exposure. Chronic toxicity, on the other hand, symptoms will appear only after the chemical has accumulated to a specific level, and it's over many exposures over time. An example of that would be lead. So signs of chronic exposure include symptoms like short-term memory loss or concentration, depression, nausea, abdominal pain, numbness, loss of coordination, tingling in the extremities. Other signs of chronic lead poisoning are like headaches, fatigue, anemia, slurred speech, and so on. All right, so make sure you do know the difference between those two terms. So it's not always easy to establish the level at which a substance is toxic, reason being variety, right? Due to differences in body mass, metabolism, lifestyles, etc. So different organisms will vary in their response to a particular toxin, and that includes like different species as well. So there's something called the lethal dose 50. This is a common measurement of the toxicity of a substance. It's done by its lethal dose 50, so LD50. This refers to the dose of a chemical that will kill 50% of the population to which it is applied. So this LD50 for a chemical, it will take into account that some individuals within the target population may be more resistant to the toxic effects of that chemical. All right, so looking at this chart here, LD50s of various chemicals, like if you look at this first one here, botulinum toxin A, this is from a bacterium, and look at the tiny amount that will be toxic versus something like dioxin, which is man-made. All right, so these first two, which are extremely toxic, are natural. They're coming from a bacteria. And then dioxin is a man-made contaminant in some herbicides and in PCBs. Nicotine is cigarette smoke, so it's got a 0.86 LD50 in parts per million, and so on. So looking at that chart, we can see that toxins that are produced by some bacteria are much more lethal than even dioxin, which is the most deadly of the human-made toxins. All right, an acceptable risk. So since not all individuals or species react the same to a particular chemical, establishing risk is very difficult, right? A dose that kills one individual may cause only mild discomfort in another. The toxicity of a chemical often depends on how the chemical enters the body as well. So for example, inhaling or ingesting a chemical is going to be much more likely to cause harm than spilling the same chemical on your skin. Okay, but again, that's general. You can't completely rely on published toxicity values to determine the effects on humans because few actual measurements have been made. There's no like human testing. Most information regarding humans is usually the result of studying some accidental exposure cases. So assumptions that humans will react to a chemical the same way that a lab rat or mouse will, those are just assumptions. All right, and we'll see an example pretty quickly here. We'll watch a couple of videos, just pausing here. All right, so next we are looking at the thalidomide issue. So this chemical, this thalidomide, was originally developed as a sleeping pill. And thalidomide, it was subjected to the usual toxicity tests and it was declared harmless. And pregnant women start to use it in the 1950s and the 1960s, and it resulted in the birth of thousands of babies with absent or extremely shortened limbs. So their arms and legs were either absent or they were extremely shortened. So further testing was then done on lab rats, and it was found that these rats can take doses of thalidomide as high as 4,000 parts per million ppm with no ill effect. But pregnant women who received a much smaller dose of it, only 0.5 ppm, at the wrong time during their pregnancy, they produced, children with missing limbs. All right, so we'll watch a couple videos here on this, and what we'll see is that in light of the fact that thalidomide is one of the most effective drugs doctors have for the treatment of many diseases like lupus, rheumatoid arthritis, should it be struck from the list of approved drugs because of the effects it had on pregnant women and their babies. All right, so we'll watch just a couple videos here. The first one, how one scientist averted a national health crisis. Lastly, we just wanted to look at the evaluation of risk, benefits versus drawbacks. So every chemical has the potential to be harmful depending on dose or susceptibility and how it reacts with other chemicals. So we must decide if its use is going to be more beneficial than harmful. And that's what we will see in our next video we'll watch next class.